Hi there, this is Jacob Nash Engineering Lessons. This is Unit 2.1, Lesson 9, on how to solve Activity 2.1.3 about free body diagrams. So if you notice, I'm using the same software as Lesson 1, which, if you remember, that was unfortunately muted. I don't think I'll be able to have time to redo that, but please comment if it's urgent for you to know about that, and I might be able to do it. But yeah, I just kind of pressed for time. This unit has a lot of videos, sort of, if you noticed, because even compared to the geometry lessons that I did earlier this year, this one's gonna have at least 13 episodes, or well, I shouldn't say episodes, videos, lessons. So, let's get started. So first, if you remember in the last lesson, I said about the different types of forces. Keep those in mind when we're doing this. So let's look at number 1. Okay, I guess I can't draw that high for some reason. So there is a fishbowl and a stand, and you're supposed to draw a free body diagram for both objects. You used a notation in the image as subscripts when labeling the forces. Okay. So the first, when you're doing separate free body diagrams, you can just draw a rectangle even if the shape isn't a rectangle. So we'll do the fishbowl first. So let's write FB for fishbowl. Even though the fishbowl's a sphere, we're doing a rectangle. So always, on all objects, there's going to be a gravity force. There might be more than one, as we'll see in number 2, but there also might just be one. That it's always going to be the object itself. So first, there's a force of gravity, Fg, down, and it said in the problem that it wants us to specify where the force is coming from, and it's coming from the fishbowl. So we can say FB. I mean, technically it said do a subscript, but that's just what I had to do. So there's also a force up. This is also a force that will be the case for all objects. There is a normal force, Fn, and it is of the stand, because remember, normal forces are just basically the surface, and the surface of the stand that's below it is causing it to not just completely fall down, because if there was only a force of gravity, it would be unbalanced, unbalanced, and it would fall down. So that's it. That's all you have to do for the fishbowl. It's going to be a little bit more complicated for the stand. Let's do S for stand. Well, sorry that I didn't do S for that part, but that's okay. So there's going to be a force of gravity down, Fg, of the stand. That's, like I said, that's always what it's going to be, because the object itself brings itself down. But there's also going to be another gravity force down, and it will be of the fishbowl, because the fishbowl is on top of the stand. That's why. And then, like I said, there's going to be a force up, a normal force of the ground, because we're assuming that the stand is resting on the ground, because let's draw this over here. So this is the fishbowl. This is the stand. That's what it looks like in the picture. And then it's on the ground. So, let me write that. That's why, because this is going up here, and then up here, and then the forces are going down, but it's balanced. So that's why the fishbowl and stand aren't going to move. That's it for this problem. Let's look at number 2 now. Now, let's see. Let me try to erase this. Okay. So number 2 is more complicated, because it involves more than one force, but also, or more than one object, really 3, and then, or 4 actually. So we have to do 4 free body diagrams for this one. So let me draw what this looks like. So we have a stand. Is that what they call it, a stand? Yeah. Then we have a log here, a log here, and then a log here. And they call this log 1, log 2, log 3, and then stand. We need to make a free body diagram of log 1, log 2, log 3, and the stand. Let's start with log 1. Oh, I have the stylus and things about to fall off of it. Let me see if this works better. Okay, then. So, like I said, there's always going to be a force down. The gravity force, and what's causing it to go down? Log 1, because that's always what will happen, because it's itself. Now, there's other forces also. There's also going to be one up, which is the normal force, like with the fishbowl problem. That's because of the stand. Now, if you notice, you basically need to make an arrow at any part where there's a contact with a different object. So there's a contact with the stand here, contact with the stand here. There is, and then there's also wait a second. Oh, well, the places where it contacts a different surface is going to be where there's a normal force. But if there's something on top of it, it's going to cause there to be a gravity force of gravity. So not only is there going to be a normal force up, there's also going to be a normal force diagonal this way from the stand once again, because the log is touching in 2 different spots. There's another force though, one more. If you noticed, right here, log 2 is resting on log 1. So there's going to be a gravity force, not down, but in this direction, from log 2. So that is the free body diagram of log 1. I'm going to have to erase this. Please look at it before I do. Now, let's do log 2. Log 2 is a little bit more complicated. First, we should always do the gravity force of itself. Then, we also have another force. There is a gravity force, another gravity force. But before we do that, let's actually do the normal force. So far we've always done normal forces for things that contact it. But this time the stand doesn't contact it. So that means that there is not going to be a normal force of the stand. There will be a normal force of log 1 because of this. So let's do that. There's also going to be a normal force for log 3 because they touch right there. And it's going to be in this direction. So notice it's pretty much just opposite of the direction that it's in. So let's do normal force of log 3. And then there's also going to be a gravity force of... Oh, I'm sorry, I messed this up. There is not a gravity force of log 2. There is a gravity force of log 3 and 1. I'm sorry about that. Here we go. And let me explain why. So, yes, there is always a gravity force coming down from an object. I mean, or else log 2 would go into space, but we're only listing 1 and 3 because of the orientation of these logs. So if you notice that log 1 and 3 are kind of holding it up, that's the reason why. So that is actually it for this free body diagram. So please please look at it before I erase it. Now, let's do log 3. There's going to be a gravity force down of log 3, because yes, it's not being held up like log 2 was. Then there's going to be a normal force up. So this one's kind of the same as, pretty much just a mirroring of log 1. It's pretty much the same. So there's a, of the stand, there's a normal force, and then there is also another stand normal force because of there's a normal force opposite to those directions because there's 2 spots where it touches. Then there's also a normal force of log 2 that is in a southeast direction because of the way that the logs are set up. Or sorry, not normal force, gravity force, because it's on top of it. There you go. That's log 3. We'll just stand last, which is probably the most complicated, but you can still do it. So I know we've been doing a rectangle, but let's do actually just the shape of the stand. So here we go. We have stand. First, there's going to be a gravity force down of the stand. There's going to be a normal force up of the ground. I'll just say G. And then there's other forces also. Because the logs are resting on it, there's going to be more gravity forces. For log 1, there's a gravity force. And for log 3, there's a gravity force. There's not one for 2, because once again, it's not touching the stand. There's other forces, but this time they're not going to be normal or gravity. They're going to be push and pull forces. So there's going to be one this way, FP of log 1, because of that log 1 is resting on it, and then one this way also that is of log 3. And that is the free body diagram for the stand, and that is problem number 2. Let's look at the next problem. Okay. Alright. So, now we have this. We have 2 rings and then 2 cables that are holding up a stoplight. There, kind of good. Now it says we don't need to make a free body diagram of this pole up here. We only need to do it the rings, cables, and stoplight. Let's start with the 2 rings. So let's make it a circle, R1, and then another circle, R2. Okay, so first, as usual, we have a gravity force down of ring 1. Same thing here. We have a gravity force down of ring 2, because that's what this is. Now, another force we have is a normal force in the opposite direction of where the cable is connected. So, right here. Normal force of cable. And then we have one more force that is in the exact direction as of the cable, which is opposite of the normal force we drew, which is going to be a tension force of cable 1, and then for this one, cable 2, because it's connected to cable 2. Just so we know what I'm talking about, this is ring 1. That's ring 2. Ooh, didn't turn out good. This is cable 1. This is cable 2, and this is stoplight, which we'll call S. So, that's the free body diagrams of the rings. Remember, tension forces only happen with strings or ropes or cables. That's why we had it on this one and not the others. Now, let's do the two cables. We can draw the cables in a rectangular way like this. And we don't have enough space to write C1 and C2, but this one's C1 and this one's C2. First, there is a gravity force directly down of the cable itself. Ooh, you know, I always do that when I'm trying to do a parenthesis and then C, I mess up because it looks the same. And then cable 2. Do it again. Then we have a tension force. First, a tension force that's in the direction of the ring, which the ring is connected at the end of it. So we have a tension force of ring 1 here, and then tension force of ring 2. But we have other tension forces also, because we have a tension force this direction and this direction, and they're both of the stoplight, because that's where the stoplight's connected. Ooh. And there are not normal forces for this one, because of where the cables are set up. They're not resting on anything. They're holding up something. Now, we'll do the stoplight free body diagram. We can do a rectangle and then S. We have the force of gravity down by the stoplight itself. Then we have two tension forces that are this direction and this direction. A tension force of cable 1, and then a tension force of cable 2. And there you go. That is problem number 3. Let's look at the conclusion questions now. So I don't think I'm necessarily going to write it down on here, but I'll say it. So, why is it important to create free body diagrams? Well, it's important so that engineers can consider the various forces on an object and find out whether the object can function properly. So, if the forces are not stable, then it might collapse, and that would be bad. So engineers need to consider that. Then we need to sketch a free body diagram of a person sitting in a car seat. Okay, we'll first do that, and then we'll answer the next part in a minute. So let me draw the person. Try to do good. Okay, and then seat. Seat, person. And you're supposed to do it of the person, not the seat. So, we'll say P. There's a force of gravity bringing the person down. That's why they're not floating up. there is a normal force up because they're sitting down on the seat. And then there's also one to the left because it's opposite of where the seat is. Because the person is touching the seat here, but also resting their back on it. They're sitting on a stool, there would not be one that direction. Now it's saying, which force arrow do you think should be the largest? The left arrow should be, because if the car is moving in that direction, so the force is going to be the largest. Cars move this way. The seats face the way the car's going, in most cases. And this free body diagram, it ties to the first conclusion question, because as soon as they drew this, they knew that you would need a seatbelt, because this force is so big that as soon as the car stops, nope, you're not going to stop. That's why you have to have a seatbelt, because you're going to crash through the windshield. So that's why there needs to be a seatbelt, so that there's another force going back this way that balances it out. So that is activity 2.1.3. I hope this video helped, and please like and subscribe if it did, and stay tuned for the next video, which is going to be on vectors.